start. So how are you guys doing? We start. Did you guys start practicing?
Yes, sir.
Oh, 1 second. I think I didn't connect my earphones. Sorry. I think now you'll be able to hear me a little more clearly, isn't it? Guys?
Yes, sir.
Cool. So what I was asking is, so did you guys start preparing? Preparing in the sense, did you start solving problems? Did you buy any
Yes,
extra
sir.
books? Okay, good. Still only four of you. Okay. Sunday, I thought you will sleep. That's why I made it by 10 o'clock. Even I wanted to sleep. So that's why it was 10 o'clock, but still people are coming late. So people in all your schools, the portions are over. Have they finished their portions, syllabus?
No, sir, not yet.
Not yet. So actually, I was praising you guys to Akila, saying that they are improving a lot. The classes are very good. Like even though the strength is less, I don't feel like the strength is less because you keep on responding, right? So all these things I was telling, I was praising. Right? 11th kids are actually a problem. Like 11th, they didn't start the JEE batch yet, but in the CBSE section, like my class is okay. My class is completely all right. Like they are very much engaging. But for physics and mathematics, I think it's chaos. They're not even opening their mouth. It seems it's very difficult actually. Like looking at a camera, actually looking at myself and speaking is like if there is no response from other side, it's the what to say the interest of giving you information goes. That's what is gonna happen. That's what will happen. Right? But thankfully, like you are nice set of students. Like you are all responding. Good, nice. And yeah, I can see a lot of improvement in academic wise also. Like even though it's been very few number of classes, right? But I feel you have improved. Like there are a lot of things which you didn't know and you grasped it and you're able to do it. Is a nice sign that you are on the right path. Good. Okay. Okay. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, cool. I think we have everybody on board. I think we can start. So guys, are you ready? Let's start.
Yes, sir.
Yeah, cool. So we have been seeing conformational isomerism, if you can remember, right? So we finished your configurational isomerism. So configurational, we know there are two types, structural and stereoisomerism. So we saw everything there, right, in depth, all these things we saw. We even started with conformational isomerism. So I told you that conformational isomerism is going to arise because of
C single bond.
CC single bond.
Rotation of bond.
Yeah, correct, right. So because of the capability of CC single bond to rotate, right? So obviously I can have different orientations of atoms in space. So by that we'll be getting conformers or conformational isomers. So we saw how to represent them, right? How I'm going to get different conformers. Say for example, if I take normal ethane, the simplest of all compounds, I was able to get only two major conformers. That is, one is eclipsed, another one is staggered. So in eclipsed, you will see, like, I hope you remember how the representation was. If you look at it from this side, you will be able to see only 3 hydrogen atoms because the other 3 hydrogen atoms are exactly going to coincide with these 3 hydrogen atoms, right? Okay, and then the next one was staggered, and that everything will be apart, right? You will be able to see all the 6 hydrogen atoms clearly, right? So that is my staggered. And then when I took the example of I think 2,3 no, butane. We just took butane, right? So we took butane, right? So other than the normal staggered and the eclipse conformation, we got something in between also. So what is it called as?
Skew, sir.
Good, right? We have something called as skew structures, which is neither neither staggered, neither nor eclipse, but it is somewhere in between, right? Okay. So now what I want you to do is I want you to draw all the possible conformations for 2,3 dimethyl butane. Go for it, right? Like obviously you will get millions of possibilities, but again, whatever can be distinctly studied, those things I want you to go for it. Go for it. 2,3 dimethyl butane. Draw the all the conformation structures on your notebook. Guys, are you able to hear? Because I got a call.
Yes, sir.
Okay, thank you. So yeah, so you can go on with drawing the conformations for this 2,3 dimethyl butane. So preferably you can start with eclipsed, right? And then rotate the bond to an angle of 60 degrees. One more, you can 60 degrees, something else. So like that you'll be able to do. Okay, so I think this time is sufficient. So we know the structure. So this is what is 2,3 dimethyl butane. So we'll try to draw it in the form which we have seen, right? Say again, I'm going to take these two carbon atoms, obviously, right? Fine. So the first carbon atom, second carbon atom, and I'm going to change my marker. Okay, right? Say if I take this carbon atom, I have one hydrogen and two methyl groups. Say I put methyl group, hydrogen. Okay. So again, if you go to the other one, I have same thing. So I will start with eclipsed. That means all the corresponding groups are going to exactly coincide, right? So if I do that, say I put one methyl group here, another methyl group here, and I put my hydrogen atom here. So this is my perfectly eclipsed structure, eclipsed, right? Okay. So then if I rotate it through say 60 degrees, the back carbon atom by 60 degrees. So you will be getting something like this. So I'll fix my first carbon atom, CH3, CH3, and H. So if I rotate the 60 degrees, so you'll get the methyl group here, this methyl group will come here, and this methyl group will come here, and the hydrogen atom will go here. Yes, no problem, right? So do you think it is going to be eclipsed? Sorry, this is going to be staggered?
No, sir.
No, right? Fine. So we'll call it as skew, or it is also going to be called as gauche structure, Gauche, gauche structure. Let me write the other one this side. I have enough space. If you're not able to see me, it's okay, no problem. So if I write again through 60 degrees, so what will you end up with? H, right? So if I rotate through another 60 degrees, so this methyl group will be eclipsed along with this CH3, and this will be this side along with the hydrogen, and this hydrogen would have gone to the methyl group, right? So again, do you think this is going to be what is that? Staggered? Absolutely not. So again, this is going to be another skew structure or Gauss structure, right? So people, what you're trying to understand here is, right? So for 2,3 dimethyl butane, you cannot exactly get a perfectly staggered conformation. That is the information which you have to get from this diagrams, right? So however, again, if you go for another 60 rotation, what will happen? This methyl group will come here, this methyl group will come here, and the hydrogen atom would have come here. So anyways, so again, you will be getting only a skew structure, right? But we can talk with respect to, we can talk staggered with respect to two of the groups if you take into the picture. For example, if I talk about these two methyl groups, right? So these two methyl groups here are actually staggered because they're exactly opposite, right? But again, these two are skew, right? So like this only we'll be able to speak if I go to 2,3 dimethyl butane. There you cannot get an exactly perfect staggered conformation, right? So that is the information we can take from this, right? You will have perfectly eclipsed, no problem. But all the other structures, whatever you will get, will be skew or Gauss structures. But still, in those skew or the Gauss structures, with respect to two of the groups, I can speak whether it's staggered or not. That I'll be able to. Is that okay? Right? Cool. So that is about straight chain compounds. Okay. Now the same thing will happen in your cyclic structures. Okay, acyclic compounds, sorry, alicyclic compounds, the same kind of things can happen. But again, I'm not going to call them as eclipsed skew or Gauss or staggered there. It is going to be completely different. Okay, so let me move on to that. Right, we'll see what happens. Okay, so people, right? So we generally write, for example, if I have cyclobutane or like we say cyclohexane, for example, cyclohexane is going to look like this. Like this is how we generally draw our cyclohexane structure on our paper, right? But it is actually not going to look like this at all. Literally, it is never ever going to look like this. Okay, it is going to be completely different, right? And why that is going to happen is because of something called as strain in the molecule, right? All the cyclic structures, right? All the cyclic structures have a problem, right? The problem they have is basically this strain or stress, they call it, right? So what do you mean by this? Where this stress or strain is coming from, right? So we'll try to understand that first. Okay. So we'll come back to cyclohexane later. We'll take a simpler cyclostructure. We'll take cyclopropane. Okay, we'll take cyclopropane. Okay. Now this carbon atom, right? Tell me what is the hybridization of the marked carbon atom? What is the hybridization of, and not only marked, any of these carbon atoms? What is the hybridization?
sp3.
Yeah, sp3, right? Obviously, you have 4 bonds, you have 2 more hydrogen atoms coming. So I told you how to find the hybridization, right? So let's remember that when you don't have any double bond or triple bond, definitely it is sp2 hybridized, sorry, sp3 hybridized. When you have one double bond, it is going to be sp2 hybridized, and when you have a triple bond, it's sp hybridized. Okay, or else I think I gave you a formula to find out the hybridization. I gave you a formula for steric number, right? Steric number is equal to number of atoms bonded to the central atom plus the number of lone pairs in the central atom. So you will very rarely see lone pair on carbon. So generally it will only be the number of atoms bonded to the central atom. So in this case, you can see that steric number is 4. 1, 2, 3, 4. That is 2 hydrogen atoms and 2 carbon atoms attached to each of the carbon atoms. So making all the carbon atoms sp3 hybridized. Okay, fine. So sp3 hybridized, no lone pair. I know the shape is going to be tetrahedral. For example, if I compare with methane, for example, right? So this is my methane. This is how the exact structure will look, right? So obviously we know this is coming towards you, this is going inside. All these things we know. So this carbon atom is also sp3 hybridized, no doubt about it, right? Okay, but if you look, so okay, fine. So we'll forget about this. Now coming back here, now tell me what will be the bond angle for the structure. Bond angle in the sense I'm asking about this bond angle or this bond angle or this bond angle, right? What will be the bond angle?
109.8.
109.8, 109 degree, 109 degrees 8 minutes, or generally I call it as 109.5 degrees. Okay, correct, right? So that's my, generally we call it as a tetrahedral angle, right? So tetrahedral angle will be 109 degree, 109.5 degrees, or 109 degrees 8 minutes, right? Something like that. Okay, fine. So we understood that. Okay, so this is predicted by my VACPR. You hope you remember you studied something called as valence shell electron repulsion theory in a chemical bonding. We'll see it again, don't worry, but you already studied it. So this is actually predicted when I have sp3 hybridization, right? And if I have no lone pair on the central atom, definitely the shape is going to be tetrahedral shape, right? And the angle will be, bond angle would be 109 degree 5 minutes. This is all is predicted by VACPR. Okay, so the prediction is based on what? Prediction is basically going to be based on stability, isn't it? Stability in the sense I am definitely going to have so many 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here. So I have to make sure that the repulsions between these electron pairs are going to be minimum, right? So in order for the repulsions to be minimum, they have to be certain distance apart, right? And if you put them in those particular positions, you will be getting the bond angle as 109 degree 5 minutes, and that is only then it is stable. Okay, only then it is almost free of repulsions. Okay, right. Now that's this all be understood. Now going back to my cyclic structure here, right? Now what do you think will be the bond angle here? Forget about its carbon. Like if I have a triangle like this, right? What will be the angle there?
60 degrees.
Exactly, right? So it's obviously all these are carbon atoms, or it is basically an equilateral triangle. All the lengths and all the angles will be same. So this angle here would be 60 degrees. Oh my God! Hey, look at this. I have sp3 hybridized carbon. I have sp3 hybridized carbon, but the bond angle here is 109 degree 5 minutes. Sorry, 109.5 degrees. But here it is going to be 60 degree. No way close. Almost even less than the double, but not exactly, almost double, almost less than half, right? So this is the reason why I have this strain in the molecule. Okay, it's because the cyclic structures are not able to meet the bond angle criteria for a tetrahedral structure, right? So this, for all cyclic structures, will generally have this strain because then the bond angles are not going to be equal. It will be very very, how to say, I have to be in this position, right? But it's very obviously you cannot keep it. How long will you keep it, right? You will keep it for say 1 hour, max 2 hours, 3 hours. If I keep on keeping like this, definitely at some point I may lose it. But if I have to sit, keep my hands in some comfortable positions, right? Definitely I'll be able to stay for more longer time. And the same goes here, right? So that is the most stable position. So this molecule will stay. I mean, this molecule will be very stable, but this is not so much, right? I have this perfectly calling, this is called angle strain. Okay, this is called angle strain, right? That's because the bond angles are not going to be equal. Okay, so when I go for cyclobutane, now what do you think will be the bond angle?
90.
Yes, 90 degrees. Okay, again if I go for cyclopentane, it'll become little more closer, like maybe it will be around 95, right? And say if I go for cyclohexane, it will be around say 103. Okay, here you can see almost it's like going to be 103 or 101, even I can call it as 105 like sometimes, right, depending on the substituents. Okay, so you can see that as the what is that, the cycle, the membered ring, the number of members in the chain, not chain, the ring increases, right? You can see that the bond angle is little more getting closer and closer and closer to the bond angle which I want. That is 109 degree 5 minutes, right? But you will see that this is okay. This is almost getting closer. But if I go for cycloheptane, right? When I go for cycloheptane, that is 7-membered ring, you will see that the bond angle will be more than 109 degree 5 minutes. Okay, so again I'm repeating, when you till now you saw 60, 90, 105, you can keep it, right? So 109, sorry, 103, so it is little getting closer and closer to the bond angle which I want. But if you expect that the cycloheptane, the 7-membered ring, will be exactly 109 for 5 degrees, no, it is not going to be like that. It is going to be more than 109 degree 5 minutes. Okay, so that again is unstable. Okay, that again is unstable. So that kind of thing, when you have bond angle greater than 109 degrees, 109.5 degrees, that is called torsional strain. Torsional, right? When you have bond angle sorry, more than 109.5 degrees, the another type of stress or strain will come, that is called torsional strain, right? So whenever the bond angle is less than 109.5 degrees, it is going to be called as angle strain, and if it is greater than that, it is going to be called as torsional strain. Okay, so basically all cyclocompounds, right, are actually going to have some kind of stress or strain in them. Okay, so which makes the CC single bond rotation more evident, more prominent, more dominating in the case of your cyclohexane, not cyclohexane compounds, cyclocompounds in general, right? So what you see in case of your aliphatic straight chain compounds, there whatever you see is single bond rotations. Here I'm going to have very, very huge bond rotation such that the structure which you see here is not going to be the structure, right? In reality, if you look at it in the microscope, the structure of these molecules, right, this structure is never going to be like this. It is going to be something very different. Okay, so we'll see what happens. How is it that the like we will primarily concentrate on cyclohexane, because you like what to say, you cannot do much, you cannot do much about this cyclopropane, cyclobutane, and cyclopentane because of some reasons which you don't have to know. It is far beyond the this thing scope of 12th class. But what I have to tell is there is nothing much you can do, right? Even though the single bonds are going to rotate, there is nothing much that these molecules, that is cyclopropane, cyclobutane, and cyclopentane, can do much about it. They are going to have the strain, but still they are going to be little stable. Obviously less stable than the aliphatic compounds, but cyclohexane has some capabilities, special capabilities. Okay, so because of this CC single bond rotations, I am actually going to get very prominent conformations I'm going to arrive at for cyclohexane, right? So we'll see what are those. Okay, right? So you have to know what is angle strain, you have to know what is torsional strain, and because of this, it is going to be more prominent. That is the CC single bond rotation, the conformations are actually going to be more prominent. That's what you have to understand. Okay, cool. Okay, so again, as I told you, this is not going to be the structure of cyclohexane, it is going to be something else, right? So I have basically I would say 4 different types of conformations possible for cyclohexane. I'll just list it out now, right? So I have something called as chair, I have something called as half chair, and I have something called as boat, twisted boat. Anything else? Yeah, so these 4, right? These 4 are the different types of conformations possible. From the name itself, you can understand what kind of shape I'm going to get, right? The first one is going to be in the form of a chair. Second one is half chair, boat, twisted boat. So yeah, so these are the different kinds of conformations I'll be able to get, right? And out of this, right? The most stable one, right? Like even in your aliphatic compounds, we said that staggered is most stable, the most stable conformation compared to eclipsed because of repulsions, right? So here also we are going to say that something is out of these four, something is the most stable one. The most stable one is my chair. Okay, I'll give first rank to this, right? And second rank to my twisted boat, third rank to half chair, and the least stable of them all is going to be boat. Okay, sometimes questions can come from this also. Arrange the different conformers of cyclohexane in the order of stability, right? So you have to know chair is the most stable one, then comes twisted boat, then comes half chair, and the least stable one is going to be boat conformation. Okay, so we are not going to concentrate much on these three, right? Actually, not we are not going to almost deal with nothing about these three because they are not important. But chair, since it is the most stable one, majority of the times you will see, if at all you view cyclohexane under the microscope, right? You will be seeing only this structure, mostly 95% of times. Okay, very rarely you will be able to see any of these three because chair is the most stable one, right? So we'll concentrate on first chair. Then, if at all, I'll just give you information about how they look. That's the thing we'll be able to see about the other three things. Okay, fine. So we'll concentrate on this chair. So how it looks. Okay. Okay. So people will find it little difficult if at all first time they're going to draw these structures because you need some practice definitely, right? So I will help you. I'll give you some tricks to draw how to draw the cyclohexane chair. Okay. So what you do is first you draw one parallel line. Okay. Or I would say not even a parallel line. You draw a parallelogram. Okay. You draw a parallelogram. Okay. So to this parallelogram, since it is a chair, right, I am going to have a rest for my head. My rest, you would have seen some chairs will have headrest, right? And it's a very sophisticated chair that it is also going to have a footrest. Hope you know what is a footrest. In your foot, something will pop up and you can keep your foot on that. Right. Okay. So this particular parallelogram, I'm going to draw a headrest and a footrest. Is that okay? Right. So now how are you going to do it? Right. It's very simple. So make sure that this, and I'm gonna draw a line, right? This line and the line which I'm going to draw is almost 90 degrees. Okay, something like this. Okay. Okay, once you draw this, now you can just join. Oh, wait. Take one more marker. Right. So you draw a line like this, and then you join these two. Bear with my diagrams. Okay. So this is the headrest. You can even keep it as footrest. It's all about how you imagine it. I am looking like I'm lying like this. My head is here. So if at all you can even call it as footrest. Doesn't matter. So anyways, this is my headrest. Okay. Now, okay. Then for this, I have to draw a footrest this side. So obviously the footrest should point down. The headrest should point up. Right. Definitely. Right. So again, I do the same thing here. I draw a line. I join it. Done. That's my footrest. Okay, then what you do is you remove this line. The parallel lines you have drawn for the parallelogram, you just remove it. Okay, so this is the structure of cyclohexane chair. Is that okay? Right? Draw a parallelogram, draw headrest, draw a footrest, remove the lines, and you will end up with the chair. Is that okay? Right? So very simple diagram. Now, but this is not it, right? There are other things which you have to know, right? So obviously, all the vertex points represents the 6 carbon atoms that are going to be there in the cyclohexane ring, right? But you have to account for other things also, right? You have to account for hydrogen atoms or say some other groups are present, right? Obviously, each of this vertex will have 2 more bonds. We know, right? Each of the carbon atom will be attached to 2 other carbon atoms, and 2 more groups should be there, right? So that 2 more groups, you must be very careful how you are going to put it, because the bonds are going to be little, one is going to be in the same plane, one is going to be coming towards you, or something like that is going to happen. But again, I'm going to make it easy for you, right? Okay, fine. So we will, okay, now please understand people, for each of this carbon atoms, for all each of these 6 carbon atoms, right, there is going to be one axial bond and one equatorial bond. Okay, each of these carbon atoms, all 6 carbon atoms will have one axial bond and one equatorial bond. Okay, so axial bond means it is going to be in the same plane, whichever plane which I'm going to talk. So this is the plane which I'm talking about. Axial bond will be in the same plane. Now there can be 2 possibilities of axial bond. One is it can point up or it can point down. Correct, right? An equatorial bond is not going to be in the same plane. It is going to be either inside or coming towards you, but that doesn't matter much. Okay, so what you have to understand is axial bond is the bond which is there in the same plane, right, as the plane of the board, right, or the plane of the paper which you're going to write. And equatorial bonds are going to be something into the plane or outside of the plane, something like that. Okay, so now how are we going to fill this axial and equatorial bonds? It's very simple, people, right? Now you state, I would suggest you either start with headrest or you start with footrest. Okay, either headrest or footrest you start with, because that is again making a reference point, something like that. Okay, now what you see is the headrest is pointing up. Correct, the headrest is pointing up, right? So fine. Again, we'll start with headrest or footrest, and right, and we are going to start first with axial bonds. We'll fill all the axial bonds, then we'll go for equatorial bonds. That is the reason why I'm telling this, because I'm going to make it easier for you. Okay, so fine. So either we'll start with headrest or footrest, and we will fill all the axial bonds first. Okay, now I'll start with headrest. You can even start with footrest, right? So I'm starting with headrest, and what I see is the headrest is pointing up, right? If you see the headrest is pointing up, the axial bond should also point up. So the axial bond here is going to look like this. That is my axial bond. Okay, right. Now coming back here to the footrest. Footrest is pointing down, right? So you are going to put the axial bond pointing down. Down. Okay, axial bond pointing down. Okay, now what I'm going to do is you are going to, so now you have put the bond up, so you are going to go for alternate, all the next carbon atom, and you are going to put the axial bond pointing up or down alternatively, in the sense, so you have this carbon, for this carbon atom the axial bond is pointing up, so for this carbon atom the axial bond is pointing down, and you have put the axial bond pointing down. For the next carbon atom the axial bond is pointing up, and obviously the next one is pointing down automatically, right? And this is pointing down, so the next one should point up. Oh, I have missed this one, I'm sorry. So the axial bond is pointing down, the next carbon atom the axial bond should point up, pointing up, the next one should point down, the next one is pointing up. Yes, very, very simple. So again, I repeat what I just did. I made sure that I started with headrest or footrest, right? And I'm going to start filling only axial bonds. Okay, so in this, headrest is pointing up, so I put the axial bond pointing up, right? The footrest is pointing down, so I have put the axial bond pointing down. And for all the other carbon atoms, just put alternate up and down the axial bond. So here it is pointing up, next is down, up, down, up, down, up, down. Cool, right? Now after this, filling equatorial bond is very, very easy. Okay, so what you're going to do is, wherever you have put axial bond pointing up, put the equatorial bond pointing down, and wherever you have put axial bond pointing down, put the equatorial bond pointing up. Very simple. Exactly what it is for axial bonds, exactly opposite for the equatorial bonds. Very, very simple. But you have to make sure that whenever you draw the equatorial bonds, please make sure that somehow you are maintaining the tetrahedral shape, little bit, like that you have to keep in mind. Okay, fine. So what I'm going to do, say axial bond is pointing up, so equatorial bond should point down. So this is my equatorial bond. Okay, that is my equatorial bond. So as you can see, right, almost I'm maintaining my tetrahedral shape. So somehow I draw the equatorial bonds like this. So that means this is not in the same plane, people. It will be actually coming outside the plane. but I'm representing in 2D structure. Okay, so this is my equatorial bond. Okay, next. So here, axial bond is pointing down, so equatorial bond pointing up. Right. Equatorial bond pointing up, right? Axial bond pointing up, equatorial bond pointing down. Axial bond pointing down, equatorial bond pointing up. Axial bond pointing up, equatorial bond pointing down. Axial bond pointing down, equatorial bond pointing up. Down. That's it. Any doubts? Okay. So what I did, again, I just give a very quick concise of what I did. I drew the cyclohexane chair. How I drew the cyclohexane chair? Draw a parallelogram, draw a headrest, draw a footrest, remove the parallel lines. Done. Then you are going to fill for each of the carbon atom one axial bond and one equatorial bond. So I suggest that you start with axial bonds, okay, and you start either with headrest or footrest. Okay, right. So whenever the headrest is pointing up, so you put the axial bond pointing up and footrest pointing down, so axial bond pointing down, and alternatively fill all the axial bonds pointing up and down alternatively. Done. And whatever you did for axial bonds, just do the exact opposite for the equatorial bond. That means if the axial bond is pointing up, equatorial bond is pointing down, and vice versa. That's it. That is how I get my cyclohexane chair confirmation. Any doubts? Any questions?
No, sir.
Okay.
No, sir.
So I assume that there is no question. So people, now what you can do is, there is something called as okay, we'll see all that later. Fine. So this is how I draw the structure. Okay, right. So we have seen that cyclocompounds can also exhibit geometrical isomerism, isn't it? Right. So I told you, if at all you have, say, 1 and 2 carbon atoms are having methyl groups, right? So these methyl groups can either be cis to each other or trans to each other, depending on how they are oriented. If both of them are pointing away, or if both of them are pointing towards you, it is going to be called as cis, and one of them pointing away, one of them pointing towards you is going to be called as trans. Okay. So what we'll try to do now is try to incorporate the geometrical isomers into this cyclohexane chair. Okay. Now, questions I have seen definitely coming. Okay. But it's pretty easy also. Okay, we'll see what we can do. Right. So I'm gonna keep this with me because I can every time I don't want to draw it. Okay. So let me start. I will start with cis 1,2 dimethyl cyclohexane. Okay, I have cis 1,2 dimethyl cyclohexane. So we know how to draw it. Right. So now this is my planar structure. Definitely, this is not how it's going to look. Okay. So 1,2 dimethyl. Right. So and they are given it as cis. So definitely both of them should point away, or both of them should point towards me. Let me put either of the things. Say I put them pointing away, CH3, and this CH3 is also pointing away. Cis. No issues. Okay. So now, how am I going to incorporate this structure to this? Right. Now, people, please understand, pointing away, pointing towards axial, equatorial, there is literally no connection. Please remember that, right? People will tend to, okay, pointing away means axial, pointing towards means equatorial. Absolutely not. No, right? So it is all about whether the bond, whether the particular axial bond is pointing up or whether it's pointing down. Same goes with equatorial, whether it's pointing up or pointing down. That is what is more important. Okay. So the thing is, whenever you are going to incorporate this structure here, you just have to look at this. It is cis, means either, there can be again two possibilities. How you have two possibilities, both of them pointing away or both of them pointing towards you. Here also you can have two possibilities, both of them pointing up. Doesn't matter whether it is axial or equatorial. Again, I repeat, it doesn't matter whether it's axial. It does matter, but for now, right? It doesn't matter whether it's axial or equatorial. It matters whether the bond is pointing up or down. Okay. So if it is cis, right? If it is cis, both the bonds, that is both the methyl groups, should point up, or both the methyl groups should point down. And obviously in trans, we can expect what it is going to be. One of them pointing up, one of them pointing down. That's how it is going to be. So now we'll try to incorporate it here. So cis, both of them should point up or both of them should point down. Now it's better to draw with starting with headrest. I prefer headrest. You can actually start with any of the carbon atom here. But again, adjacent carbon atom is what you have to take. That you keep in mind, right? So let me start with my headrest because preferably that's my favorite position. So I'll start with that, but there is no restriction. You can take any two carbon atoms as 1 and 2. You can take this as 1 and 2, 1 and 2, 1 and 2. You can do anything, right? Okay. Now, so cis, I'll put it, for example, say if I put this CH3 pointing up. So in this carbon atom, axial bond is pointing up. Doesn't, again, I told you, axial or equatorial doesn't matter. Only whether it's pointing up or pointing down, that's what matters. Okay. Now, you can either take this as the second carbon atom or this as second carbon atom. Again, there is no restriction. I will take this one. So if the methyl group is pointing up, right, I have to make sure that the other methyl group is also pointing up because it is cis. Say I'll put the other methyl group here. Okay. You can see in this case, axial, equatorial bond is pointing up. That's what I told you, that the axial or equatorial doesn't matter. Okay, so one CH3 pointing up, the other CH3 is also pointing up because it is cis. Cool, right? Okay, now what you're gonna get here is basically you have one methyl group in the axial position, the other methyl group in the equatorial position. Okay, right. But there is something for stability. Okay, again, how do you have different stabilities for different conformations in your straight chain compounds, right? Here also I have some criteria for stability. Okay, the criteria for stability the criteria for stability in this chair structures is that the bulky groups should be there in the equatorial position. Okay, there is only one condition, very simple condition. The condition is the bulky groups. I hope you know what are bulky groups. If I have hydrogen, that is not a bulky group, but methyl group is a bulky group. But if I have methyl group and ethyl group, methyl group is the most bulkiest group, or in other words, I can say the most bulkiest group. The most bulkiest group should be there in the equatorial position. Okay, only then I would say it is stable. Again, why it happens, because my bulky groups, if it is going to be, already see this particular entire chair is in the same plane, right? And if I'm going to put the bulky groups in the same plane, that is in the axial position, right, I'm going to have so much repulsions. And that's the reason why I make sure that they point either out of the plane or inside the plane so that the repulsions are lesser. Okay, that's the reason why I put the most bulkiest group in the equatorial position for my stability. Okay, right. So in this case, you can see there is one axial bulky group and there is one equatorial bulky group. Okay, now in this case, you have put both of them pointing up, right? Now to the next possibility. The next possibility can be both of them should be pointing down, right? And if that's the case, what I'll do, so I will start with here, like I'll assume, okay, I'll rub this off, right? If you want, you can draw a separate chair. You actually, it's better, right? You draw one chair, putting both of them pointing up. Now you draw a second chair. Now both of them are going to point down. So in this case, the pointing down is here, equatorial, and the pointing down is here, and that is axial. Okay. Now what do you see here? However I do, both of them pointing up, both of them pointing down. Either way, I am getting one axial CH3 and one equatorial CH3. That means both these conformations are equally stable. Cool, right? So last case, again, both of them pointing up, I put. In that case, I had one axial and one equatorial. If I put both of them pointing down also, I'm getting one equatorial and one axial. That means both these conformations are equally stable. Cool, right? Okay, fine. Now when I go for trans, we'll see what happens. Okay, so when I go for trans, right, when I go for trans, So what I do, I just make sure that one of them is pointing towards you and one other one is pointing away from me. Done. This would have been the structure for trans. Okay. Now, this what you did. It again, it doesn't matter whether it's active, axial, or equatorial, but it matters whether the bonds are pointing up or down. Okay. Now, since it is trans, right, one methyl group should be pointing away, and another methyl group should be pointing towards. Sorry. One methyl group should be pointing up, the other methyl group should be pointing down, vice versa, right? For trans, right? Okay. So let me start with this. Okay, fine. So if I put the methyl, one of the methyl groups pointing up in the first carbon atom, the second carbon atom methyl group should point down. Okay, so up, down, down is here. I'm getting two axial CH3s, right? Okay. Now, what is the other possibility? Now I have put it in the first carbon atom. I have put the methyl group pointing up. Now I can put the methyl group pointing down also, right? So if I do that, CH3 will come here. Now it is pointing down. So the other CH3 should point up because it is trans. Now what you get? You are getting two equatorial CH3s, right? Obviously, I know what is more stable now. Definitely this is the most stable one because CH3 is the only bulky group there, right? And obviously you see that, what is it? I'm getting two equatorial CH3s if I'm going to put one of the CH3s in the equatorial position, right? Okay, now out of these two, definitely this is more stable. And if I go for comparing the stability with cis what I got, however you put, right? So however you put the methyl groups, right? You got what? One axial and one equatorial, correct? Right? Now in this case, one of the possibilities are two axial species that is definitely the least stable out of all the three we saw. Out all the three in the sense, in cis we had only one possibility. However you put one axial, one equatorial, right? And in trans you got two possibilities, that is two axial CH3s or two equatorial CH3s. Definitely the most stable one is two equatorial CH3s, and the next less stable one is going to be one axial, one equatorial, and the least stable would be two axial CH3s. And this is never, you are never going to see this happening. This will never, you will never see this happening, right? So if someone asks you, what out of cis 1, 2 dimethyl cyclohexane and trans 1, 2 dimethyl cyclohexane, which one is more stable? You can blindly say that trans 1, 2 cyclohexane, sorry, dimethyl cyclohexane is more stable. Why? Because from the conformation analysis, right, we got two equatorial CH3s, making sure that the bulkiest group is in the equatorial position. Is that correct? Everybody understood? Any questions?
Understood, sir.
Okay, right. Now, what I'm going to do is, like instead of 1, 2, I'm not going to give you a cis and trans. Okay, let me take 1, 3 dimethyl cyclohexane. Okay, now you tell me, I have cis and trans, I can have so many possibilities, I can cis possibilities, trans possibilities. Now you tell me which will be most stable. Now go for the structures, go for the cyclohexane chair, put the bulky group, you do it. Go for it. Right? I have 1, 3 dimethyl cyclohexane. I wanted to do both for cis and trans and tell me which is more stable. Go for it. See, generally, if it is going to be an aliphatic compound, we say that trans is more stable, generally, right? But in this cases, whenever you go for the cyclohexane chair, it is not always that. Now, last case, you got trans is more stable, but it is not going to be always like that. Please remember that. Okay, fine, go for it. So start with drawing the planar structure. You can probably start with cis Then go for the possibilities. I mean, draw the cyclohexane chair. So you don't have to fill all the other bonds. Just fill your first. I mean, 1 and 3 alone you fill the axial and equatorial. Okay, because again, if you, that will take much time to fill all the things, but still. Please don't
Sir,
sit idle, people. Yeah,
cis is stable, sir.
this is more stable. Yes, that's correct. This will be more stable. So hope everybody is trying. Please do not sit idle. If you're gonna sit idle, the most boring class will be organic. Okay, because you have to do a lot of structural drawing, analysis, and all those stuff. At least if it's physical, I'll be giving you only problems and you have to substitute, and maybe sometimes little trickier problems will be there. Okay, so now I think we'll try to complete it. Right. So it's 1, 3. So let me start with cis first. Okay, just randomly starting. Okay. So cis means this also should point away from me. Right. Okay. So this CH3 is not here. So what I have started with, okay, fine. So I have put the first CH3 in pointing down, right? So definitely the other CH3 should also point down is what we have to understand. Okay. So pointing down here, this is the third carbon atom, first carbon atom. Okay. So both of them pointing down and both of them are in equatorial position. So first itself I got my answer, right? But we will check. Okay, we got the answer in the sense this is the most stable one, right? Because I have two bulky groups in both the bulky groups in the equatorial position, right? Okay, let me start. Okay, now if I put both of them pointing up, again this would be the least stable one, isn't it? Right, because both the bulky groups are in axial position, right? Absolutely not the answer which we expect. Again, not the answer in the sense, not the most stable structure we expect. Okay, so that's about the cis possibilities. Now let me go for trans possibilities. Right, now trans, first position I have put the methyl group pointing up. So third position I have to put the methyl group pointing down, right? And I think the second case also, say if you put the first methyl group pointing down, in the equatorial position it will come, and in this case you'll get it in the axial position. So either way, right, you are going to get one one axial, one equatorial bulky groups, right? So obviously in this case, cis is the most stable one because you got two methyl groups in the equatorial position. Yes, right? Cool. Now what I'm going to do is, let me put wait. I have 1, not 1, 4. 1 ethyl, 4 methyl, for methyl cyclohexane. Okay. Again, I'm not giving you any cis or trans. I want you to directly get what is the most stable conformation. Again, obviously, you have to draw all the structures for checking it. Now tell me, go for it. I want you to have the most stable conformation for this. It can be the cis or trans, but again, cis again, so many possibilities. Trans maybe have so many possibilities. Just go for it. So I have one ethyl group and one methyl group, and obviously you know ethyl group is more bulkier. So in this case, it might not be just the cis and trans. In trans or cis, one of the conformation is going to be more stable. right? That's how you will get the answer. So what will they give is, they will just give this compound the most stable conformer of this compound, and they'll give you 4 choices. Right? You just have to tick which one is the most stable one, and obviously what you have to look for: ethyl group, preferably ethyl group and methyl group should be in the equatorial position. Right? At least if not, at least the ethyl group should be in the equatorial position. That's what we need to get.
Sir, is it trans?
Yeah, maybe. I don't know. You have to check. We'll check. Okay, fine. So let us start. Right. So okay. So I don't want to go for every structure possible, right? I will directly try to go for the most stable structure in cis and trans. Okay, fine. So if I take cis, right? So the most bulky group among these two is ethyl, right? Say in the first carbon atom, I'll blindly put C2H5 in the equatorial position because that is what is most stable, right? And since we are starting with cis, right? So my this thing is pointing down, right? My equatorial bond is pointing. Sorry. In this case, the C2H5 is pointing down. So the fourth one that is here, right? That also should point down. Okay, so the pointing down is here. So CH3 should point down. Okay, so in the most stable conformation for cis, I am getting C2H5 in equatorial and CH3 in axial. This is what I'm getting. Okay, obviously if you go for the other one, that will be less stable, because if you put the pointing up position, if you put C2H5, you will get methyl group in the equatorial position, but that is little stable but not as stable as compared to this, because the most bulkiest group must be there in the equatorial position. Okay, right. Now we'll check my possibilities for trans. Okay, so trans, again, for my most stable conformer, I put the C2H5 in the equatorial position, right? And it is pointing down. So it is, since it is trans, the fourth carbon atom methyl group should point up, right? So pointing up is here. So now what you're getting? C2H5 in equatorial, CH3 also in equatorial. Definitely, this is the most stable structure. So yeah, your answer is correct. Trans is the most stable one here. Okay, people. Now, any cyclohexane compound given to you, and if they ask you to find the most stable structure, very, very simply, you will be able to do it. Okay, any questions from this? Okay, fine. So I hope everybody is clear, right?
Sir,
So that is about, yeah.
sir, we can either start from the footrest or from the headrest, right?
Anywhere. You can even, you don't even have to start from footrest or headrest. You can just start from here also, from random position, and just count 4 carbon atoms or whatever the number of carbon atoms and put the other group. It doesn't matter where you start. You will get the same answer. Okay. Right?
Yes, sir.
Yeah. So that is about the cyclohexane, people. Cyclohexane chair. That's what we have, right? So now this is what is most important. If you get questions, you will get questions from this, or the other question I told you. Out of the 4 conformers, which is more stable, like arrange them in the order of stability. That I already gave you, right? So what you like, sometimes instead of giving the names, they will give the shapes of how they look, right? So for that information alone, I'll give you what are all the how they look. Twisted board, how they look alone, I'll give you, right? Or you can, like, but I forgot how half chair looks. Okay, fine. Please check for half chair alone how it looks. You can just type half chair conformation of cyclohexane. Maybe you will be able to get it. Or like, wait, 1 second. I myself will check. Okay, I think I can share my screen for you. Where's my Google? got the picture. 1 second, people. I'll share my screen. Then you can see it. Oh God, what happened? Okay, wait. I will come back. Where is my Zoom? Yeah. Only host can share this meeting. Oh my God. I don't have the option of sharing screen. I'm sorry, people. All these efforts went to waste. Okay. So maybe next class I'll show you. Right? Is that okay? I can draw you. I can show how the boat and twisted boat looks. Okay, something like this. Um, 1, 2, 3, 4, 5, 6. Yeah. So this is my boat. You can see, right? This is my boat structure, boat conformation, right? If it is going to be twisted boat, it's something like this. Yeah, something like this. This is my twisted boat. Okay, this is my twisted boat, and half chair. I will try to draw it, but I'm very bad at drawing as such. Okay, people. I don't want to try. Right. So only one thing is remaining. That is half chair. Right. So obviously, the three structures, whatever the thing in the options which the other structures they gave, I'm going to give, that is my half chair. Okay. So boat, twisted boat is more stable, right? So first, most stable one will be what is that? Your chair, then twisted boat, half chair, and boat. Okay. These are all the different conformations for cyclohexane, right? Cool. So successfully, we have completed all types of isomerism. Okay, done and dusted. All types of isomerism, starting with structural, and then that's so many geometrical, optical, conformational. Everything is done. What is the time? We have almost half an hour left. So we will go. We will go for the next section, right? So you can also check if you just type conformations of cyclohexane, you'll be getting all these structures. Or you can even watch beautiful YouTube videos will be there. You can watch it. Right. So we will start with my. Okay. So let me go back to the first ever class which we saw. I gave you a flow chart of how an organic reaction will happen. Right. So if you can remember what was there, I had something called as substrates. Okay. And to these substrates, I had something called as reagents attacking. Okay. And this was forming something called as intermediates, right? And these intermediates, I told you, were unstable, right? These intermediates were unstable. God, 1 second, people. Oh, right? And they will eventually form products, right? So this is the entire flow chart I gave you, right? Substrates are there. Substrates can be anything. It can be alkanes, alkenes, alkynes, alcohol, ethers, phenols, carboxylic acid, anything it can be, right? And I told you reagents can be of two types, right? reagents can be either electrophiles or nucleophiles, but we'll not concentrate on them first. And I have something called as intermediates, and this is the most important part, right? For you to, so this entire thing is what is called as the mechanism of an organic reaction. That is, if you just, if you look at this, just the reaction, you will see what are the reactants, what are the products, what are the catalysts, what is the temperature used, what is the pressure used. Yeah, all these things only we'll know, right? But there are a lot of inside things which are happening, right? And if at all you want to perfectly predict what the product will be, looking at the reagent and looking at the substrate, you need to know what is this intermediates. Okay, so this intermediates are going to be like, if at all you know what are the different types of intermediates. I have something called as carbocations, carbanions, free radicals, and other than that, right, other than that, I have something called as carbenes, nitrines, ketenes, right? So again, those are little less important, maybe for JEE Advanced, not even for JEE Advanced. Some of the reaction, for example, your Reimer-Tiemann reaction, you have studied, right? Right. So in Reimer-Tiemann reaction, there is a new intermediate called as carbenes. Okay. And what else? I don't think you know much of the reactions involving ketenes or carbenes. Anyways, we will see reactions. Okay. So we are going to study about them today. That is my intermediates, right? So we'll see what are them, like we will see how they are produced and all that, right? Okay, fine. So for me to study about intermediates, right, we have to understand these intermediates are formed because of some kind of bond breaking happening. Okay, so between CH bond or between a CO bond or a CC bond, whatever it is, right, there is going to be some kind of bond breaking happening, right? And because of that, you end up with this intermediates. And obviously, after the intermediates are formed, they're going to gain something or lose something to form the final product. But that is the next case, right? So first, what you have to understand is how and all a bond can break in chemistry, I mean organic chemistry, right? So I would say the bond fission, that is my bond breaking, can be of two types. Okay, so one is what is called as your homolytic bond fission. The other one is what is called as your heterolytic bond fission. Okay, so all these things I've already studied. I'll just quickly go through it, right? So obviously you know what is going to be a homolytic bond fission, right? Say if I have a CC bond like this, and obviously other three bonds are there. Okay, so I will represent the bonds. Okay, so if it is going to be homolytic bond, please understand. I have to really go by markers. Okay, fine. So please adjust people if it is really. Are you able to see what I'm writing, or is it too light?
A little bit, sir. It's okay.
Okay, wait. I will try another. This is my last choice. If I don't have, I'm really sorry. Okay, so I know. Okay, this is better. Fine. So I know that I have two electrons shared here. One electron coming from one carbon, another electron coming from another carbon, right? So I am going to break the bond in such a way that wherever the electrons came from, they are going to go back to their original parent atom, right? So now, like whenever you're going to go for homolytic cleavage, see, in organic chemistries, arrow marks are very, very important. Okay, so basically you will be using arrow marks in the mechanism. You will say that this goes and attacks to this particular carbon atom, or say the oxygen atom's lone pair is going to attack the H plus. All these things you will be representing with the help of arrow marks. Okay, so as I said, arrow marks are little of interesting area or very important area when it comes to organic chemistry mechanisms. Okay, so please be very careful. Okay, so I have these two electrons. So I told you that these two electrons are going to go back to their parent atoms. So how will I represent it? I will be representing with an half arrow, right? What do you see? You can see that I have put, and there's a hook. This is called a hook arrow. Okay, so this, whenever you see this kind of thing happening, that means it is going to be a homolytic bond fission. Okay, so obviously this side also it is going to break, right? So again a half arrow should come, right? So bond is broken homolytically. So this is exactly how I break it. right? So wherever the electron came from for sharing, it is going to go back to the original parent atoms, right? So what will you end up with? You will end up with this carbon atom having this single unpaired electron. Again, another carbon atom with this single unpaired electron, right? So whenever you have this odd electron species, means if you have a single electron which is not in the bonding state, which is not in the form of lone pair, or no, what is a lone pair? Lone pair means two should be there like this, right? One electron, another electron, if it is there, that is called a lone pair, right? But if one single electron is not involved in bonding, is not in the form of a lone pair, but a single electron just there, right? Whenever you see species having this kind of things are what are called as free radicals, right? This is my carbon free radical. Okay, so it is not only with carbon, I can even have this kind of things happening with water. For example, say HOH, right? Say again, I have an electron pair shared here, half arrow, I can end up with H dot and OH dot. Okay, so this is called my hydroxyl radical. This is my hydrogen radical. Okay, so this is what is example. This is what is my homolytic bond fission. So whenever you have homolytic bond fission happening, you will always end up with free radicals, either carbon or some other thing. Doesn't matter. But homolytic bond fission, how do you represent? You represent with a half arrow, like a hook arrow, right? And you end up with free radicals having unpaired electrons, unpaired single unpaired electrons, odd electron species. Okay, right. So moving on to this heterolytic bond cleavage, you will be able to guess how is it going to be, right? So hope you understood this. Let me rub it off. I will not take much of your time. I'll just finish this heterolytic and I'll stop with this because my markers are a problem, right? Okay, I'll rub this off. Okay, so in heterolytic, so for example, for heterolytic bond cleavage, you need to have enough polarity difference, or say enough electronegativity difference between the bonding atoms. Say for example, generally if you have a CC bond, heterolytic cleavage cannot happen. Say even if you have, I would say most of the times in a CH bond, also mostly, yes, there are cases where heterolytic bond cleavage can happen, but again, very rarely it will happen. Mostly, generally, it will only be homolytic bond cleavage, right? So please understand, for homolytic bond cleavage, right, I don't require electronegativity difference. But if it is there, also it might happen. If it is not there, also it might happen. But for heterolytic bond cleavage, right, there should be considerable electronegativity difference between the bonding atoms. Please understand that, right? For example, I'm telling the CC bond generally will not CC bond will never undergo heterolytic bond cleavage, right? Say if I have a CCl bond, obviously other three bonds are there for this carbon, right? So obviously carbon atom is very less electronegative, chlorine is highly electronegative atom. So in this case, you can generally expect a heterolytic bond cleavage can happen, right? Now, why is it that this is a requirement, that is I should have high electronegativity difference between the bonding atoms? Why is that requirement? Because the electrons are not going to go to, say, the one electron, last case, one electron came to one atom, the other electron went to the other parent atom. Now, in this case, both the electrons are going to go to one single atom. Okay, so you have an electron pair shared here, right? So in the homolytic bond cleavage, sorry, heterolytic bond cleavage, how will you represent it? You will represent it with a full arrow, not a half arrow. Means you will say that this an entire electron pair goes to chlorine. Okay, so you will end up, obviously, now what will you end up with? The both electron has gone here, so carbon has lost one electron and chlorine has gained one electron. So you will be getting Cl minus ion, no doubt about it, right? And you will be getting this carbon atom to have a positive charge. And this is what a carbon atom having a positive charge is what is called as carbocations, right? So these are what are called carbocations. Okay, carbon atom having a positive charge. Okay, Now you can have some cases where the carbon atom can have a negative charge also, because now in this case, say for example, there is some X which is less electronegative, or it depends on the reaction. Sometimes they can just donate the electron and leave. All these things can happen. So again, I have an electron pair. In this case, a full arrow marking towards carbon atom, right? So you will have X plus and carbon atom to have a negative charge, and this is what is called as your carbanions. Okay, right? So these three, that is three. So whenever you have heterolytic cleavage happening, you can end up with two things: either carbocations or carbanions, depending on what other atom is attached to it and how the bond is breaking. Okay, so whenever you have homolytic cleavage, you'll always end up with free radicals, and whenever you have heterolytic cleavage, you can end up with carbocations or carbanions. And the other two, that is carbenes, nitrines, ketenes, all these things we'll see in X class. Okay, and we have to understand that in a mechanism, in a reaction, there can be many types of carbocations formed, right? And obviously the product, right, is going to depend upon which is the most stable intermediate. Okay, so we know that we have primary, secondary, and tertiary, and all those things. So we will try to use certain methods to determine, okay, this is the most stable one, this is less stable, this is lesser stable. All these things we'll be able to see. Okay, so all those things, those are what are called as electron displacement effects. Okay, so all these things we'll be seeing next class, right? So any doubts, any questions till now? Any questions from anywhere, from whatever you're seeing?
No, sir.
Okay, fine. So that's it, people. That's it for today. Cool. Thank you. Bye bye.
Thank you, sir.
We'll meet on
Thank
next
you, sir.
Saturday.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you.
Yeah.
Thank you, sir.